Yeah, the floor is yours.
Thank you. Thank you, Elena, for the introduction. Thank you, everybody, for being here. Sorry for the inconvenience for the start. So, I'm Mattia Di Gangi. I did my PhD thesis at the University of Trento and FBK, also in Trento, Italy. The topic was neural speech translation from neural machine translation to direct speech translation. And the idea was to continue on this field of speech translation and improve the work with the direct speech translation model that translates directly from audio into text in the target language. And now I'm working at Aptec as an applied scientist. This work wouldn't be possible without the great guidance of my co-advisor, Marcello, Federico, Marco Turchi, and Matteo Negri, and the collaboration of all the machine translation team at FBK. Most of them are my co-authors, and anyway, we had great discussions about science with everybody. That was really important. But now, let's get into the topic. So speech-to-text translation is the task of processing audio in order for spoken sentences and translate them automatically into text in a target language. For example, here we have somebody speaking in English, and then this is processed and translated into French. There are many motivations for that. One is real-time communication. Let's say we are tourists in a foreign country, we want to speak with locals. There are already apps that are trying to do that, but everything can be improved, of course. And another example can be live broadcasting. We want to consume great content from all over the world. And now let's get to something a bit more technical. So this is a scheme of how it's supposed to work. There are different ways in which it can be implemented. The traditional way is the cascaded approach, where we have a cascade of machine learning models. We start from audio processing. This is not machine learning. These are actual classic algorithms that are not necessarily needed, but this is the usual practice. And then with speech recognition, text normalization to modify the automatic transcripts in a form that is more fit for machine translation, and then machine translation, and also other models in between, because it is a complex pipeline, actually. And in this thesis, we wanted to explore what are the possibilities of using a single model for substituting, for replacing the pipeline. The direct speech translation models, of course, are quite different from a cascade, both in positive and negative ways. So they provide a single source of errors because, of course, having multiple machine learning models means that their errors will be compound. And also, in terms of latency, here we have a single beam search, so we can achieve a lower latency. And also, if we have a single model, this is more compact and can be more easily fit on low power devices. But the drawbacks are that they need on-purpose data sets, because we need parallel data where audio is on the source side and text on the target side, and this is not very common. And also, a negative side of the models as they are presented here is that the transcripts are not a byproduct of the process. We only have the translation, and sometimes we need also the transcript. In my thesis, I covered many aspects. I started from assessing the tolerance of neural machine translation to speech translation errors, also some work on deep learning for machine translation, and then the real work on direct speech translation. But on this presentation, for time reasons, I will focus only on the right-hand side, left hand for you. So there was some work on direct speech translation before this thesis. It started on 2016, as far as I know. In 2016, some papers proved that this approach was feasible, but the results were quite poor. Then there were works by Google and other research institutions that showed that with pre-training and multitask training, it's possible to improve the performance of the systems, but they always evaluated on small test sets, like Home. And then in 2018, there was more work on pre-training and multitask training, and some more data sets were released. And the work of this thesis for direct speech translation started in the mid of 2018, more or less. And there are two main works that I want to talk about that are MustSee, that is the corpus that we released at FBK, and S-Transformer, that is an adaptation of Transformer for this task. As I said, this task requires specific data, and the situation as of 2018 wasn't great for training models. This is a comprehensive list of the data sets that were available at the time that have more than 30 hours of speech. So the largest one was this how-to from Sanabria et al., English to Portuguese, downloaded from YouTube, and then English. The second one is the AWSLT corpus, English to German, and then less and less data. So there are few, they are small, and they only cover a few languages. And for example, in AWSLT 2018, there was an evaluation for direct speech translation, and this is a screenshot of the data available. For ASR, we have significantly more audio data than for speech translation, and between machine translation and speech translation, we cannot even compare. So we decided to release MustSee, a multilingual speech translation corpus that is built from TED Talks. So all the source side is always in English, and there are 8 target languages, mostly European languages, I would say all European languages: Spanish, German, French, Italian, Dutch, Portuguese, Romanian, and Russian. And the number of hours goes from 385 for Portuguese to 504, with an average of more than 400. And for all the language directions, we provided an empirical and manual quality assessment, and also some baselines. And the data were collected so using the transcripts and the translations that are provided by volunteers in the TED website, and we ran some filtering for ensuring high quality of the data. Then there is also a second version of MustSee that expands the corpus to 6 more Asian languages. Why TED Talks? As of 2019, there were more than 3,000 TED Talks, and this is always high quality speech because it has been rehearsed many times, high quality recordings, they are high quality microphones, and there is a high topic and speaker variability. And the transcripts, as I said, are written by volunteers, and except some cases, they are quite high quality, and the same for translations, a lot of translations and constantly growing. So today the numbers are much higher. And here there are the statistics of the original MustSee. I just want to highlight here that the number of hours of speech that is considerably higher than the previous data set that I showed before. Although this is not order of magnitude, but still it allowed us to train models for some language pairs that weren't available before, and also obtain some reasonable results. And MustSee was very impactful on the speech translation community. It has been used as a training set for AWSLT since 2019. And so for the first time, it enabled experiments on larger data, not only a couple of small data sets. And I can say that after MustSee was released, many more groups started working on this field. Maybe it's not casual, but this happened after MustSee. And then new data sets followed, inspired by MustSee, for example, MustCinema, that is for subtitles, and MustSee, that is a test set for gender bias on speech translation. And you can download MustSee from the website. Then the second line of work is the one for S-Transformer. So to understand the reason, we need to talk about the input that we have. In machine translation, we start from words that are converted into embeddings. This is instead a reasonable input for speech translation. So these are not word embeddings. The difference is that here on the vertical dimension we have some frequency information. So the vertical dimension is not just random. And also, there are bidimensional dependencies that don't exist in machine translation. And then also, the local context is more informative than the sparse context. If we take features at like half a second or even 1 second space, they are not necessarily very related. So when we compute attention on this should be taken into account. And that's why in S-Transformer, that is an adaptation of Transformer for speech input. It provides bidimensional oriented encoder computation and a locally biased self-attention. There are 2 publications about this, and there is a GitHub repository where the original implementation was released, and this also helped people to start in the task. This is a schema of the encoder. The transformer decoder was left unchanged. And so on the spectrogram input, we have convolutional neural networks because they can model local bidimensional dependencies, and also bidimensional attention that I will talk about it in a couple of slides. And the idea is to also capture bidimensional large range dependencies. So this is how the bidimensional attention starts. We have our spectrogram or a higher level representation of a spectrogram. There are bidimensional convolutions inside the attention. We get a new tensor, and from this we compute the usual attention over time, and then a second attention on the frequency by transposing the tensor. So we get 2 context vectors. These are concatenated, and we apply a new bidimensional convolution on this new tensor, and this is the output. So it can capture dependencies on both dimensions and on a long range, because this is attention. And also, as I said, we are interested in the local context, and because in audio the input length is much longer than for text, and also with let's say a lower information density, we need to collect many adjacent features in order to produce a significant linguistic unit. So we propose to use this distance penalty to give a higher attention to the attention center, let's say. So from the position that are more close to the attention position, so the target position, get a higher weight, and while the others are penalized and are more difficult to attend to. And we got some interesting improvements on MustSee. We re-implemented the paper by Berard et al. 2018. So with S-Transformer by itself, using the same number of parameters, we get some improvements by training for much shorter, and then we realized that actually all the models, most of the models that were used in research for this were very undersized. So we made it larger, and the results were clearly better. And then we decided to combine the work of S-Transformer and MustSee into new applications. And so we went for multilingual speech translation. In this paper presented at ASRU, we basically trained 2 models, one for Germanic target languages, one for Western European target languages. We proposed two ways to introduce target language information on the target side. One is by concatenating a language token, as we do for machine translation. This is on the decoder. Another approach that works better actually is to sum the language embedding to all the target tokens, and this helps the model to discriminate better between the target languages. And then a second work was about the target segmentation for speech translation, because all the works until 2019, more or less, were using a character level target. Then other work started using BPEs, and there were comparisons. So all the new models were better, and we decided to study if the reason was the subwords, the BPE subwords used, or actually the new proposed models. And in the end, we saw that yes, multilingual helps. Using BP also helps a lot, maybe more than multilingual. So this way, we demonstrated that actually the segmentation was really important, and all the comparisons were not really fair, and the segmentation should have been taken into account. So to conclude, we proposed MustSee, that at the time was the largest multilingual corpus for speech translation. Now there are more corpora with more languages, but for size for a single language, I think MustSee is still the largest. And we also proposed S-Transformer, that was an adaptation of Transformer for speech translation that improved results on MustSee over time quite significantly. And we also participated to AWSLT by proposing new different techniques for training, and we saw a large improvement on this task. We, together with the community, and now the direct speech translation models are more usable, are almost on par with cascaded speech translation models. And for future directions, now there is an interest on going beyond end-to-end speech translation, incorporating multilingual and multimodal models, because not only speech, but also images can be interesting, videos can be interesting. And this can be used for subtitling, for example. There were some papers presented yesterday, and for dubbing, and I will talk about this also in my poster later today. So thank you for your attention, and I'm here for your questions.
Thank you, Mattia. It was great to have spectrograms in this conference. Really nice done. Questions? Yes. Microphone, please.
Really interesting paper, thank you. My question was, since you're using a standard transformer decoder, does it help to initialize the decoder weights with something trained on text-to-text translation, or is the input so different that it actually basically has to start over and those weights don't help?
This is something that has been tried on the literature. We also tried it. If you just take a pre-trained decoder, it doesn't work. It does a lot of training issues. Other people got some improvements by using an adapter layer before the decoder, and this helps a bit, but pre-training the encoder is the part that really matters, not really the decoder.
Thanks.
More questions? I have one, Mattia. Do you think that TED Talks are a good proxy for conversational data sets?
No, TED Talks are not conversational, of course. The real conversations are much more noisy. We don't have high quality microphones. Usually we have phones, but we needed to start from somewhere. So TED Talks was an easy way to have a good corpus, and these were what we collected. Now, people that are interested in different applications collect data. Like now at Aptec, we collect data for our applications, but that was a purely research corpus. We wanted to prove that this approach was feasible, and this was the best way to do it.
Svetlana, could you join me? You're the personal part of this success. Could you join Mattia? Mattia, it's a great pleasure to award you the Besties Award of 2022.
Thank you very much.